Hello everyone. In this video, we're going to look at 6 different ways of deriving the OLS estimates for linear regression using Microsoft Excel. So here is the data set that we have. We have the TV advertising budget as the independent variable X and sales as the dependent variable Y. And here is the scatter plot between TV and sales. So the first method that we're going to look at is simply using the intercept and slope formula, which are available as Excel built-in functions. Note that we can use the intercept and slope formula only in case of simple linear regression. That is when we have only one regressor, which is true in our case because TV is the only independent variable. So let's get started. I will use intercept. It asks for the Y vector first. So sales is our Y. Then comma X, and I hit enter. I get my intercept, which is 7.0326. For the slope, similarly, I'll type slope. Again, Y goes first as the input parameter. Then we have X, enter. So that's how we got the estimates for our beta coefficients using the built-in formula, which is intercept and slope. Once we estimate the beta coefficients, we can immediately find Y hat and U hat. Y hat is the predicted Y. So Y hat is given as intercept. Now I'm going to dollarize that so it's fixed, plus slope, again fix that, times X. All right. So 7.971, that's our predicted Y for the first observation. Note that this is the actual Y, 22.1, and this is our predicted Y. So I can calculate the same for all observations by dragging the formula. U hat stands for fitted errors or residuals, which is the unexplained part in the model, and is given as actual Y minus predicted Y. All right, so that's our residual. And so that's how we can calculate the predicted Y and the residual vectors. One of the assumptions of OLS is zero conditional mean. It means that in the population, the error terms have zero mean. The other assumption of OLS is that the regressor X and the error terms are uncorrelated. All right. Now we don't have the error terms in the sample. We have the estimates of the error terms or the residuals. However, in the sample data, when you estimate the beta coefficients using the OLS estimator, it creates the residuals in such a way that these two properties are satisfied in the sample. These two properties are enforced by OLS in the sample. So let's verify that. First one is zero conditional mean of the residuals. So I can take average, or you can also take sum, doesn't matter. If it is 0, it will be 0 for the average and it will be 0 for the sum as well. So average of residuals is equal to 0. All right. So OLS calculates beta coefficients in such a way that these properties are enforced on the sample data. The second one is correlation between the regressor and the residual vector. So let me find out the correlation between X and the residual vector. So in vector algebra, you'd say that they are orthogonal. You see the correlation is 0. The other way of saying this is that X vector and the residual vector are perpendicular, orthogonal, so that the dot product is 0. All right. Now, there is another formula using which you can calculate the slope coefficient. All right, it uses the covariance between the independent and the dependent variable and the variance of the independent variable, and the ratio of those two is given by the slope coefficient. So let's verify that. In the numerator, we have covariance. Now here you can use the population covariance or the sample covariance, doesn't matter. Or the only thing you have to ensure is that you are using the same version for the variance in the denominator as well. It means if I use population covariance in the numerator, I'll use the population variance in the denominator as well. So covariance between x and y divided by variance of x. So I've got variance, I'll use population variance here of x. Enter. So I get the same number here that I got for the slope coefficient. All right. Now let's look at the second method of how to estimate the beta coefficients. Now we are going to use the matrix-based formula for OLS estimator. If you look at this formula, its beta hat is equal to x transpose x inverse x transpose y. Now this is the most general form of OLS estimator, and you can use this to calculate the beta coefficients in case of multiple linear regression as well. So all we need to do is define the x and y, and we can get the OLS estimates. Y is straightforward. Y is the dependent variable vector, which in our case is the sales. For x is called the design matrix, which consists of all the independent variables that you have. So in our case is just the TV vector. On top of that, you have to add a constant vector of ones and build that matrix. So basically, the design matrix in our case consists of these two columns. All right, the first column is just a vector of ones, and the second column is our usual independent variable. If you have a multiple regression case, then first you need to have the vector of ones followed by how many regressors you have in your model. All right, so this matrix right here is our design matrix X. Now for the ease of calculation, I'm going to rename this as X. All right, I'm also going to rename the sales vector as Y so that we can closely follow what formula we are using. Now please note that this formula returns beta hat vector. All right, so to use that, I will select these two cells equals to. Now I'm going to start building up this formula on the right hand side step by step. First, let me build up x transpose x, which is a matrix multiplication of x transpose and x, right? So M mult, that stands for matrix multiplication. Transpose of x goes first, comma x. Okay, so this part is x transpose x. Then I need to take inverse. So I'll use matrix inverse, which is minverse of this quantity. Now I'm done till x transpose x inverse. Then multiply this entity with x transpose. So I will use again M mult, multiply this entity with x transpose, so transpose of x. All right, now I just have to multiply this with y. So again M mult, multiply this with y. Now here, very important is to press Control Shift Enter, because this will return a array or vector. Control Shift Enter, and here I have the estimates. And note that the estimates for intercept and slope match with our previous result. The next method we will use is the Excel data analysis tool pack. So if you go to data tab on top, here you will have a data analysis tool pack. If you click that, it has a lot of statistical analysis tools available for you. One of them is regression. Now if you don't have data analysis tool pack, it's very easy to install that add-in. All you need to do is go to File, then click Options, click Add-ins, and then click Analysis Tool Pack, and then click Go. So here you have to check the analysis tool pack and click OK. Since I already have it on my dashboard, I don't need to do it. So So to run regression analysis using the toolpack, you have to click data, then data analysis, click regression. It asks you the dependent variable and the independent variables. So first we have to specify y, which is in our case sales. Next we have to specify all the independent variables. So if you have more than one independent variables, you just have to click and drag all of them. Here I have only TV as one regressor, so I'll just select that. Notice that here you don't have to additionally create a vector of ones and include that in X. You don't have to do that here. Here you are just specifying the actual regressors. Excel automatically will calculate intercept for you. All right. So I specify Y and I specify X. I can choose to see the output in this sheet or in a new sheet. So here, if you click output range, maybe this cell, so it will give you the output starting from this cell on this sheet. If you don't want this on the sheet, then you can select the new worksheet option. All right. So let me hit OK. Now here is the regression output. So it gives us the beta coefficient estimates here. And if you see, these values match our previous result. On top of that, there are a whole bunch of other statistical outputs such as R-square, adjusted R-square, then t-statistics, p-value against each of these coefficients, overall f statistic. So we'll get to all of these in a separate video. Right now we are focusing on estimating the beta coefficients, and here they are. And they are the same as we got in the previous two methods. If you don't like huge reports as the data tool gives you, you can instead use the linest function in Excel, which is our next method. So linest stands for linear estimator, which is what the OLS estimator is, and it gives us all the critical statistical outputs in a very compact fashion. So basically, linest function returns a 5 cross k plus 1 matrix. K is the number of regressors, and of course if you include one intercept, then we have k plus 1 parameters to estimate. Alright, so let's go through the interpretation of different items in this table. In the first row, we have all the beta coefficients. The second row gives us the standard errors of all those beta coefficients. In the third row, we have R-square as the first item, and then the standard error of regression. In the fourth row, we have the F statistic, which is the overall, gives you the overall significance of the model, and then the degree of freedom. In the final row, we have sum of squares of regression, also known as explained sum of squares, followed by sum of square of residuals. So in our case, we only have one regressor, so k is equal to 1. So we will get a 5 cross 2 table as the output. So let's do that and try to interpret the results. So I'm going to select this entire cell equals to linest known y's is this, comma, known x is our TV vector. Now it lets you choose. If you want to force the intercept to be 0, you can do that by clicking on this option. But if we want to estimate intercept normally, then we click on this option. So I'll click the latter, so we get the intercept as is, comma. If you want all those statistical outputs that we just discussed, then you select this option, return additional regression statistics. If you don't want those, then select the other option. I'm going to select this option, so I get all the statistical results. Bracket close. Again, since the output is an array, so you have to press Control Shift Enter. Now let's see. So here are the results. The first row are the beta coefficients. And if you recognize, this matches with our previous result. But very, very important tip here is that the coefficients are ordered in the opposite way. if you see, the first coefficient is not the intercept. It is actually the coefficient of the TV vector. All right. If you notice in the table, it says m sub n, which means the first coefficient is for the last regressor. The second one is for the penultimate. And in the end, you see the B actually represents the intercept. So basically the coefficients are arranged in the reverse order. So from this table, if we want to extract slope, it will be the first one, okay? And intercept would be the second one. Now, one of the advantages of Linest over the Excel data tools is that the report that comes out of data tools is static. It means if you update the input data X and Y, the reports do not update to reflect the new input. But in case of Linest, the output is dynamic. So if I change X and Y, then the output of Linest will also change. So if you're working in a dynamic input environment, then I would recommend you use Linest. All right. The next method we are going to look at is directly minimizing the sum of square residuals, or SSR, using Excel solver. So if you recall, the OLS estimator is derived by minimizing the sum of square residuals, and we do have an analytical closed form solution for the OLS estimator, but just for the purpose of the exercise, we will use the Excel solver to solve to minimize the SSR and get the beta estimates. Now in real life, not always we will have the closed form or analytical solution for optimization problems. Sometimes we have to resort to numerical algorithms for optimization, such as gradient descent and etc. So here in Excel also, when we invoke the Excel solver, behind the scenes it will use the numerical optimization to solve for the optimal beta estimates. So first we have to define SSR, and a SSR is nothing but sum of square residuals. Beta 0 and beta 1 are the estimates that I want Excel to solve for. So these are also called as decision variables in the regular optimization world. SSR is sum of squared residuals. So I'll use sum SQ. Sum SQ basically takes a vector or a list of numbers and returns sum of square of each of the items. So that is precisely what I want. So sum SQ of the residuals here, enter. Right now these are 0, so I'm getting so whatever is Y, the same is the residual, and this is my SSR. Now I want to minimize SSR by choosing the optimal values of beta 0 and beta 1. So we go to Excel solver. Now minimize, I select minimize this cell, right? That's my objective function, by changing the variables, these two. All right, I want to change beta 0 and beta 1 in such a way that SSR is minimized. And there are no more constraints. I will use the GRG nonlinear algorithm in Excel and hit solve. Solver found a solution, and the solution matches our expected result. So these numbers match with all the previous algorithms that we looked at. The last method that we are going to talk about is called maximum likelihood estimator. It's probably the most popular estimation technique in statistics. The idea of maximum likelihood estimator, or MLE, is to focus on one variable in the dataset which presumably has a distribution. It could be multiple variables as well. But if there is a distributional assumption on one of the variables, and we have the sample data of that variable in front of us, then what we do in MLE is estimate the parameters of that distribution in such a way which maximizes the likelihood of observing that sample. In our case of simple linear regression, we can enforce normal distribution on the error terms. It's not a bad assumption, although normality of error terms is not one of the core assumptions that you need to prove that OLS estimator are the best unbiased linear estimator. However, for all practical purposes, we almost always assume that error terms are normally distributed, and this assumption is needed for hypothesis testing and building confidence intervals. So we can assume that these sample data points of error terms are coming from the same normal distribution. Now this is the normal density of one normal random. Now all of these data points are coming from this normal distribution. Now what parameters we have here? We have sigma, which is the standard deviation, and the mean is 0 because error terms have 0 mean. All right. Now if this is the density of one sample data point, then the density of the entire data set will be the product of individual densities, because these draws are independent. All right. So the joint likelihood of the entire data set will be product of the individual likelihoods, and I have that here. So when you multiply this for each of these individual sample data point, the term in the exponent will just get added up. All right. And all of these follow the same distribution with the same sigma and same parameters. All right. Now for optimization standpoint, we take log so that this ugly product actually gets simplified into a summation, right? So when we take log of joint likelihood, we get a sum of three different terms basically. Now this shows you that the log of joint likelihood is a function of three different parameters. One is sigma, and the two others are the beta coefficients. So here what I have done is replaced ui, which is the residual, with the actual y minus the predicted y. All right. Okay, so the traditional MLE route would be to differentiate this expression with respect to each of the parameters that we are trying to estimate. So for example, we will differentiate this expression with respect to sigma and set it as 0. Differentiate this expression with respect to beta 0 hat, set it as 0, and then differentiate with respect to beta 1 hat and set it as 0. You'll get three equations, and we have to solve those three equations to get the estimated values for beta 0, beta 1, and sigma. All right. Notice that when we differentiate this expression with respect to beta 0 hat and beta 1 hat and set them as 0, in those two equations, the sigma, which is in the denominator, will only act as a scalar. And the equation equates to 0, so really the value or the estimate of sigma does not affect the estimates of the beta coefficients. Since our focus of this video is estimation of beta coefficients, let's use an intelligent estimate of sigma to start with. So how can we use an estimate of sigma that is intuitive, that is natural? Well, we have the sample data points, and the estimate of sigma would be the sample standard deviation, right? That's natural. So let's use that. Standard deviation sample of the residuals. This is our estimate of sigma, and we did not follow the traditional MLE route, but the route would be to actually differentiate everything and set them as 0 and solve the equations. And there is a catch here. We'll talk about it in a bit. So I have an estimate of sigma. Now let's estimate let's find out the likelihood of each of the data points. Now we know that all of these data points come from this normal distribution. So I'll use the normal density. So norm distribution, this is the value, right? Observed value, comma, mean is 0, comma, standard deviation is this, which is fixed for all the observations, comma, I don't want the CDF, I want the probability mass function, which is the density. Enter. So this is the density of this data point, assuming that it comes from a normal distribution with this as the sigma. So let me calculate the individual densities. Now let's take the log of the density. So this is log of likelihood. Next, we calculate the sum of log likelihood. So I have already calculated here. It's basically just sum of log likelihoods. All right, so this is the, right now the value of beta 0 and beta 1 are 0, and this is what I'm getting as the sum of log likelihoods. Now I want to maximize the sum of log likelihoods by changing these two decision variables, which I want to estimate. So let's use Excel solver. Maximize sum of log likelihoods by changing these two cells and press solve. So Excel has found a solution, and not to be surprised, the solution matches our previous results. And the standard error has been updated. As I told you before, the standard error will depend on the estimates of beta 0, beta 1, not the other way around. Because only when you estimate beta 0 hat and beta 1 hat, these are residuals reflect accurately, and the estimate of sigma will depend on the value of the residuals. Now I will leave as an exercise for you is that the estimate that we got here for sigma is not what you'll get if you actually differentiate this with respect to sigma and set it as 0. The MLE estimate gives you a biased estimate of sigma. So the answer that you will get if you actually differentiate and set it as 0 is not the sample standard deviation version, you'll get the population standard deviation version. So what answer you will get is standard deviation population of this. All right, so this is what you'll get as the MLE estimate. Now note that this choice of sigma does not affect the estimate. So just to illustrate that, let me choose this as, let's say, 5, all right, which is independent of the residuals. Now if I use a fixed value of sigma, let's see what happens to the estimates of beta 01 and beta 1 hat. Let's try to solve this again. So everything is the same. All I need to do is just press solve. You see that the estimates that I got is exactly the same as previous. And that is obvious because if you look at the structure of the joint likelihood function, the estimate or the value of sigma really does not affect the MLE estimate of beta 0 and beta 1 hat. That's why you get the same estimates. That's all for now. I hope you enjoyed these 6 different approaches to solve for OLS estimates using Microsoft Excel. Thank you so much for watching. If you liked the video, please subscribe to this channel to get latest educational content on statistics, finance, risk management, and analytics. Also, if you are a finance professional and looking for a certification in data science, log on to peaks2tails.com and check out our prep course for Finance Data Professional, which is a global certification offered by FDP Institute. Experience a new way of learning complex mathematical and statistical concepts with rich visualization in an easy-to-follow Microsoft Excel-based environment. Take advantage of our mind maps and Excel-based hands-on modeling sessions.